I'm from Pakistan Institute of Engineering and Applied Sciences, and I'm a bachelor student, senior bachelor student, and my supervisor is Dr. Muhammad Irfan. The title of my bachelor dissertation is Engineering the Kerr States and Nonlinear Resonators. The contents which I'll follow to cover up my presentation are, firstly, I will go through the background, what is my motivation behind the project, and what is a quantum computer processor, and how we use those Kerr states in the quantum error correction, and what is a two-photon drag method. Then I will briefly explain methods, the Hamiltonian experimental realization of our method, and then I will describe the results, and I will show that we have created a stabilized Kerr states, and those Kerr states can be used in a universal quantum logic theories. And then I will present the overview and the future directions of my presentation of the project. So what is a quantum computing processor? Exactly analog to classical computers, where the information is encoded as a discrete units. In the quantum computer processor, the information is encoded as a discrete units or the superposition of those units. For example, information can be encoded in transform qubits, which are the artificial atoms which have two energy levels, and we can encode information in upper or the lower or in the superposition of those states. And the information can also be encoded in the number of photons in the cavity. So if you encode the information in a transform qubit, mean the artificial atom, then there are two types of errors, which are the main errors. So the relaxation error and the phase Philip error. The relaxation error is actually a bit Philip error. And if you encode the information in a number of photons in the cavity, then there is one type of error, which is single photon loss error, where the annihilation operator is the loss operator for that error. So when we have errors, we have to correct that. There is a general scheme for the quantum error correction. What we do is that we encode the logical qubits in the subspace of many physical qubits, and we do not take into account the hardware-specific errors. But for that, we have to use much larger circuit depth for the error correction scheme. So we take the hardware-efficient quantum error correction scheme into preference. In that, what we do is that we encode the logical qubits into subspace of many physical qubits, and we take hardware into account. Specific errors means if we are considering the cavity photons for the encoding information, then we have to firstly encounter those loss operators. And what is our method is that we have to reduce the qubits and the depth of the circuit. So there are many methods where we encode the information. There's a GKP code, and there's a binomial code, and there is one that is coherent stateless code, which is our project mainly. So what is our main motivation is that by using those coherent states as a basis, we can exponentially suppress those bit flip errors. And there is a linear increase in the base flip errors, but we can also encode, we can also encounter this as well. But what is the challenge? The challenge is that it is already being used in general purpose. But the challenge is that how to generate those coherent states, and how to stabilize that coherent state, and then how to manipulate those coherent states for the quantum information processing. So the method which we are going to present, which I am going to present, is that by using the two-photon drive on the Kerr nonlinear resonator KNR, we can efficiently prepare those Kerr states, and they are stabilized, means they are robust against single photon loss, and they can eliminate the Kerr phase evolution due to Kerr nonlinearity. And there is a method which is quantum transition-less driving, through which we can non-adiabatic initialize those Kerr states or the Kerr coherent states. But there are also two methods which were presented by Likhtas and Berhami, and the links which are given in the following slide, in the bottom of the slide, and those are also methods through which we can create those Kerr states. In the Likhtas, what he does is that he take the dispersive case for dispersive case for the qubit and the cavity interaction, and Berhami uses the dissipation while stabilizing those Kerr states. So before going into the extensive slides, what is a coherent state? Coherent state is a state which has a well-defined phase and amplitude, and in the quadrature space, it is presented as in the given figure. and alpha, which is amplitude, which is coherent state, is stabilized by input power, which oppose the damping. And when we encode the information, when we are going to encode the information in the cat states, we have to encounter that damping, so that there shouldn't we can encode the information in there. So what are coherent states? Coherent states are actually quasi-orthogonal. They are not quite orthogonal. For large alpha, we also need large alpha because we have to stress those bit flip errors. So for large alpha, they become quite orthogonal, and we can use as a basis those coherent states as basis, and they are the eigenstates of loss operator. Remember, loss operator was the error when we encode information in the cavity form. So this is also eigenstates of loss operator. So what is our system? Our system is that we put the transform qubit in the cavity. Transform qubit is just for there to induce Kerr non-linearity. And we apply the two-photon drive. What is the two-photon drive method? Two-photon drive method is that we have to apply the drive field whose frequency should be 2 times the resonator frequency. And when we plot that Hamiltonian of the system, we can see that there are two degenerate eigenstates. The coherent states are the eigenstates of those Hamiltonian. So the alpha and the amplitude of coherent state is based on the EP over K. EP is a drive field, and the K is a Kerr non-linearity. There is a competition between these two states. In the general case, there is competition between the damping and the input power, but here the competition is between the drive field, which is actually a damping, which is actually an input field, and the Kerr non-linearity to stabilize that coherent states. So this is experimental realization. We take a cavity and we put a flex pump qubit over there. Flex pump qubit is just for the parametric amplification or to induce the Kerr non-linearity. And this is a micro size system. So in the basis, the cat states, even cat state and the odd parity cat states, they are represented as a computational basis of log sphere, and similarly the alpha states are minus alpha. So what are our results? The results, you can see easily that when we have plotted Hamiltonian, we can see that we have achieved a 99.3% fidelity of the operation, and there is a bit rotation in the eigenstates of those of this Hamiltonian. And this first plot, upper plot, is plotted for when we take the K Kerr non-linearity positive, and the drive field is scaled as 16 times of K. And we have also encountered the loss operator in it. And when we taken K as a negative, we can see that fidelity also reduces, and the drive field is 4K times. The main issue is that we didn't achieve the 100%, is that we can achieve 99.99% when we increase the subspace numbers. And actually, the main issue is that for the cavity is an infinite Hilbert space. So we take into account only 30 subspaces, and when we take further 40 or 60 subspaces, we can achieve 99.99% fidelity. So here, what I have taken is that I have adiabatically initialized vacuum state, and I evolved it to the KNR Hamiltonian. It's presented in the previous slide, and the loss operator in the upper figure, the K kappa, which is a single photon loss, is equal to 0, and the EP field is exponentially, it's a adiabatically increasing drive field, and we can see that we have achieved a cat state. And when we take into account the fidelity of the operation is 99.84%. And when we take into account the single photon loss error, we have reduced that fidelity to 98%, but still it is high for the use of 2 qubit gears of the single qubit gear. And the figure is plotted at t is equal to 0.5 over k. Sorry. And going beyond adiabatical initialization, there is a way to non-adiabatic initialize that cat states. Here we actually explored the mechanism of quantum transition diagram, which is presented by some authors. And what we do is that we actually we have to introduce a new Hamiltonian, which is a shortcut Hamiltonian. What we do is that we initialize that cat states, and we try to achieve it in a minimum time. So here we initialize in the upper figure, you can see that we have initialized a vacuum state and evolved it through the KNR Hamiltonian, and the EP drive field is 4K, which is a non-adiabatic term. And we can see that those cat state is distorted. That cat state cannot be called a cat state. You can see in the figure, there's so much distortion. So how we encounter is that we introduce a shortcut Hamiltonian. That Hamiltonian corresponds to additional two-photon drive, whose expression is given EP prime. EP is a two-photon drive, which is in our system, and EP prime is a new drive field which corresponds to a shortcut Hamiltonian. And we have achieved a 5 times faster those cat state, and the fidelity of operation reduces to 97%, but it is still so much better for the 2-qubit operations. So in this, we can see that we have stabilized, or to see that can we produce those coherent states as a stabilizer or not. In this, we have presented those cat states. For a larger time, you can see that at t is equal to pi by k, that's a lossy KNR. I mean, we didn't count the two-photon drive. We can see that the contrast in the linear function of those cat states also reduces, and there is a reduce in the separation of those cat states. That's due to the Kerr non-linearity and the dephasing effects, the single-photon loss. But when we take into account the two-photon drive, we can see exactly that at t is equal to pi by 8k or t is equal to pi by k, we have achieved a stabilized cat state. The fidelity of the cat state reduces to 76%. We can achieve much better those cat states. I mean, we can increase the fidelity of the operation through taking some other parameters. And there's a research. So in the qcMAP gate, it is one type of method through which we generate those cat states. In that, the author left us. I have presented it in the previous slide. So what he does is that he takes into account the dispersive case between the qubit and cavity. In that, we introduce a superposition state, and then the coherent cavity state is a coherent state, and in the composite state, we evolve it through Hamiltonian, the dispersive Hamiltonian, and we evolve it for t gate time. And we displace the cavity state with alpha, and then applied controlled rotation gate. Controlled rotation gate is that it is only applied when the number of photon is vacuum state, 0. And we then displace the cavity state with minus alpha to re-origin that cat state, and then the final state is the cat state. But the main point to represent over here is that when we take into account this specific case, we achieve a distorted cat state. In the figure B, you can see that the cat states are distorted, and it is. And when we take into account the two-photon drive into this method, we have achieved not distorted cat state, but a perfect cat state. So we can use that coherent states, or consequently the cat states, in the computational basis of log sphere. We can manipulate them. The universal set of gates are Z gate, X gate, and entangling gate. How we apply a Z gate? Z gate is simply we have to lift the degeneracy of those degenerate eigenstates of the Hamiltonian. 0 or 1 here is even parity cat state and even odd parity cat state. And for that, we to lift the degeneracy, what we do is that we apply additional single-photon drive, and the Hamiltonian of Z gate is represented as Z is equal to H0. H0 is actually a two-photon drive Hamiltonian of KNR, and EZ is an additional single-photon drive. And the NOT gate, due to strong confinement, we have seen that for the large alpha, the bit flip errors exponentially decrease. So due to strong confinement, and for that confinement, we cannot apply X gate as simply. There are two methods for the application of X gate. The first is that we have to turn off the two-photon drive and evolve the KNR Hamiltonian under the given system, and through which the system will bit flip, and we can apply X gate. And the other method is that we can introduce a detuning between the two-photon drive and the resonator. And the fidelity of the X gate we have achieved is 99.7% when we take single-photon loss. So to complete the set of universal quantum gates, we have to apply entangling gates. For the entangling gate, we take the two KNR Hamiltonians, and we couple it through an additional single-photon drive, which we have used in the Z gate and the application of Z gate, and the resonator is initialized in the composite states of those two KNR and in the composite states of cat states, and we have achieved the fidelity of the entangling gate at 99.99%. So just an overview of what we have did is that we have generated those coherent states, mean we evolved the Fock state of the cavity through the KNR, and we have generated those coherent states. And how we stabilize is that there is a competition between the Kerr non-linearity and this two-photon drive, and we have stabilized those coherent states for the specific phase and amplitude of two-photon drive, and we have manipulated those cat state for the source side quantum logic gates. We have applied, we have shown the application of Z gate, X gate, and entangling gate. So what is the future direction? So future directions can be, we can study a triple photon or in general the n-photon driving methodology, in how it affects the fidelity of the operations, or can we achieve some better results or not. And we can teleport those cat states to transmit the encoded information. We have achieved in the previous slide that the fidelity reduces to 76% for the time t is equal to 5k times, but we can teleport those cat states to check out the fidelity of the encoded information. And the future direction can be, we can map these cat states and apply the algorithms, and the Grover's algorithm mainly. And so thank you. So what are the questions? So one of the question is why we apply, where we are going to apply Grover's algorithm for the application of this cat state. There's no specific reason behind the Grover algorithm. Actually, the Grover algorithm is an optimization algorithm, and it is much, it has much applications in the optimizations. So there's no specific reason we can apply those cat states for the Shor's algorithm, or even the phase estimation algorithm, or the FFT. There's no such basic specific reason. It has much application. That's only one. And the other question is, all right. One of the question is why? I mean, how we apply a two qubit gate algorithm, two qubit gate operations. Okay. For the application of two qubit gates, what we do is that we take into account the two KNR, mean two cavities, and the two transmon in the cavity and the expected cavity, and we couple it through the single-photon drive, and then we apply a two qubit gate. And it's much there is a much research going on in how we can apply a 3 qubit gates or the Toffoli or some other gates, in how much we can get fidelity of the operations. The general idea is that we take two KNR and couple it through some coupling field, and then we apply a 2 qubit gate. And I have not done research on that. Entangling view is a 2 qubit gate. We have shown in the previous slides. Right. Thank you.